The objects we interact with every day are easily measured in familiar terms: pounds, ounces, kilograms. But try to apply those same macroscopic rulers to the quantum realm, and the math breaks down almost immediately. Take a single atom of carbon-12. If we insist on using standard kilograms, we're forced to work with a mass of 1.992647, preceded by a string of 26 zeros. Managing that many decimal places makes even simple equations impossible to calculate. To make atomic physics functional, researchers had to step away from the kilogram and build a custom-scaled ruler. To understand the smallest parts of our universe, we need measurement tools that actually fit the dimensions of what we are looking at. Physicists solved this by adopting a highly specific standard of measurement, the atomic mass unit, or simply U. To find a starting point, they took a single carbon-12 atom and mathematically fractured it into 12 equal pieces. One of those twelfths became the new base unit. This unit replaces nightmarish decimals with clean numbers. It allows the masses of most elements to be expressed as values very close to whole integers. With U as a standard, the atomic nucleus became a territory that could be mapped and measured with high-precision instruments. Equipped with this new unit, researchers used mass spectrometers to weigh different elements with extreme accuracy. Based on the parts they were finding, scientists expected every atomic mass to be a perfect whole number multiple of the hydrogen atom. But the data from their experiments didn't fit the theory. Chlorine was a particularly strange outlier. Instead of a neat integer, its atomic mass was measured at exactly 35.47 U. This non-integer mass signaled that the interior of the atom was more complex than a simple collection of identical units. The explanation for the chlorine discrepancy was the discovery of isotopes, variants of the same element that share chemical traits but have different physical weights. A natural sample of chlorine is a mixture of two distinct weights, a lighter version at 34.98 U and a heavier version at 36.98 U. These aren't distributed equally. In nature, 75.4% is the lighter isotope, while the remaining 24.6% is the heavier one. When we calculate the weighted average of these two groups combined, we get the value of 35.47 U seen on the periodic table. What looks like a single uniform substance is actually a blended mixture of different isotopic masses. We can see the most basic version of this structure by looking at the simplest element in the universe, hydrogen. Hydrogen also contains different isotopes, including heavier variants like deuterium and tritium. But if we isolate the lightest and most common version, which makes up 99.985% of all hydrogen, we find the absolute core of the atomic nucleus. This stable, positively charged building block is the proton. By using the value provided the numerical foundation used to calculate the composition of every other nucleus in the periodic table. We started with a scale problem where macroscopic kilograms were too large and clumsy to be useful. Adopting a custom atomic unit didn't just simplify the math, it allowed us to identify isotopes and realize that elements are actually blends of different weights. This measurement system gave us the precision needed to finally define the exact mass of the proton. Through the refinement of these custom units, the study of the nucleus moved past rough approximations into a world of high-precision measurement and predictable components.